Hello everyone, my name is Rahil Valani and I've recently finished my PhD from Monash University. Today I'll be presenting our work on a new type of locomotion which we call stop and go motion that arises when droplets are placed on a vibrating fluid bath. This work was done in collaboration with my supervisors Anya Slim at Monash University and Tapio Simula at Swinburne University. In 1831, Michael Faraday observed that when a container filled with liquid is vibrated vertically, then the free surface of the liquid becomes unstable to standing waves. These standing waves, which we now know as Faraday waves, they emerge above a certain threshold of the driving amplitude. And these waves typically oscillate at the subharmonic frequency, so half the driving frequency. Now, below this Faraday threshold, the surface remains completely flat, even though the liquid is vibrating vertically. In 2005, Yves Couder and colleagues in Paris showed that just below this Faraday threshold, a droplet of silicon oil can be made to walk on a vibrating bath of the same liquid. So as you see in that video, each time the droplet bounces, it locally excites damped Faraday waves around itself. The droplet then interacts with these waves on subsequent bounces to propel itself horizontally at a constant speed. One thing to note is that the droplet is generating the waves. So if the droplet were to disappear, then the waves would decay and the surface would again become completely flat. Hence, the droplet and the wave coexist as a particle wave entity. So the Walker is a macroscopic realization of a particle wave entity, and it has been shown to mimic several features that were previously thought to be exclusive to the quantum realm. In experiments, we discovered that instead of driving the bath at a single frequency f, if we drive the bath at two frequencies, f and f on 2, with a relative phase difference delta phi, then droplets that are much bigger in size can now walk, and they walk much faster, and hence we call these superwalkers. So the superwalkers that emerge at two frequency driving can be more than double the size of single frequency driven walkers, and they can walk up to more than triple their speeds. Now, the superwalking behavior is sensitive to the phase difference between the two driving frequencies. So as you see here in this plot, so on the x-axis we have the phase difference delta phi, and on the y-axis we have the walking speed of the droplet. So as you see, depending on the phase difference delta phi, the droplet can either be in the superwalking regime, or it can bounce or even coalesce with the bath. And even within the superwalking regime, we see that the droplet's walking speed varies significantly. In experiments, we also observed that if the two driving frequencies are slightly detuned, so instead of driving at, say, 80 Hz and 40 Hz, if we instead drive at 80 Hz and 39.5 Hz, then we observe a stop and go motion, or SGM for short. So as you see in this video, in this locomotion, the droplet walks for a while, then stops, then walks for a while again, and this cycle repeats. So today I'll present the result of a numerical study that we have done to understand this stop and go motion of superwalking droplets. So let me start by briefly describing the theoretical model that we'll use to simulate the droplets. So the vertical dynamics of the droplet are modeled using this equation. So it's basically an F equals ma equation. So on the left-hand side, we have mass times acceleration in the vertical direction, and on the right hand side we have all the forces acting on the droplet. So the first force here you see is the effective gravitational force that acts on the droplet in the frame of reference of the vibrating bath. And then the second force, Fn, is the normal force that the droplet feels when it contacts the underlying waves. So this interaction between the droplet and the underlying waves is modeled using a spring and a damper system. Now, similarly, in the horizontal direction, we also have an equation of motion of the droplet. So we have the forces that are acting in the horizontal direction. We have the drag force acting on the droplet. So this drag force is a combination of two different components. So the first component is coming from the drag that the droplet experiences during contact with the bath. And then the second term is the aerodynamic drag. Now, the force on the right-hand side is the force or the kick that the droplet receives when it impacts the bath. So this force is proportional to the gradient of the wave beneath the droplet. So combining this equation of the horizontal motion and vertical motion and coupling it with the wave profile h of x comma t, we can simulate the droplets. So if you'd like more information on the model, you can have a look at our recent paper in the Journal of Fluid Mechanics. All right, so here's the plot again showing the dependence of the steady superwalking speed on the phase difference delta phi. The marker here are the experimental data and the curve is from simulations. Now, when the two driving frequencies are slightly detuned, the driving acceleration takes on this form. So two frequency driving at frequencies f and f on 2 plus epsilon can be thought of as a slowly varying phase difference that varies linearly in time. So what this means is that in this plot, we traverse the delta phi axis either from left to right or right to left, depending on whether the epsilon is positive or negative. So this results in periodic traversals of the bouncing regime and the superwalking regime that results in the stop and go motion. Now, the two different colors that you see on the curve, the red and the blue, they represent the different bouncing modes of the droplet. So to understand the bouncing mode and the vertical dynamics of the droplet, we generate bouncing mode plots by tracking the vertical position of the droplet's south pole, so the red dot, the vertical position of the bath, the black dot, and the wave height directly beneath the droplet. And we plot these as a function of time, which will result in a plot where you can visualize the vertical motion of the droplet as a function of time. So the blue part of the curve represents the droplet bouncing in what we call a 1-2-1 mode. So in this mode, the droplet impacts the bath once every 2 up and down motions of the bath, or alternatively 1 period of the driving signal. While in the red part of the curve, the droplet bounces in a 1-2-2 mode. So in this mode, the droplet impacts the bath twice every 2 up and down motions of the bath. Now, in these plots, the gray region represents the times at which the droplet is in contact with the bath. So for a 1-2-1 mode, during one period of the bath, you see a single gray bar representing one contact, while in the 1-2 mode, you see two gray bars representing two contacts per period. Now, the 1-2-1 bouncing mode is crucial for superwalking, as the droplet in this bouncing mode is bouncing at a frequency f on 2, so half the driving frequency, which is the same as the frequency of the subharmonic Faraday waves that the droplet excites on each bounce. Hence, in this mode, the droplet's bouncing is in resonance with the wave it excites, so it can excite those waves efficiently and superwalk. We have explored the stop and go motion, or the SGM, in the parameter space spanned by the detuning parameter epsilon and the droplet radius r. We uncover a variety of different types of SGM in the parameter space. For small droplets, we find that these droplets either don't walk or they undergo irregular SGM. So in the irregular SGM, the droplet erratically switches its walking direction and traverses unequal distances after each cycle. Intriguingly, for larger droplets, we find that we get a back and forth SGM and a forth and forth SGM. In the back and forth SGM, the droplet reverses its walking direction every cycle, while in the forth and forth SGM, the droplet maintains the same walking direction after every cycle. Let's have a look at the back and forth SGM in some detail. All right, so let us start with the back and forth SGM. So in panel A, we have the walking speed of the droplet as a function of the evolving phase difference for one cycle of the back and forth SGM. So here the light blue curve is from the SGM simulations, while the background multicolored curve is from the steady superwalking simulations. So in this SGM, we find that during the acceleration stage, when the light blue curve is below the steady walking curve, the droplet bounces in a 1-to-1 mode. So in this mode, the droplet is efficiently able to excite the underlying waves and accelerate during this stage. Now, once the light blue curve exceeds the steady superwalking speed, the deceleration stage begins, where the droplet starts receiving kicks in the direction opposite to its direction of motion. Now, during this time, the droplet also transitions to a 1-to-2 bouncing mode where it can no longer excite those waves efficiently, and the wave field of the droplet starts to decay as well, as you can see in panel E, which is showing the gradient of the wave field beneath the droplet. So you can see that it increases and then it starts to decay once the droplet transitions to the 1-to-2 bouncing mode. So at this point, two effects are taking place. So the droplet is receiving kicks in the direction opposite to its motion, and the wave field itself is also decaying, which is decreasing the magnitude of the force that the droplet feels from those waves. So in the back and forth SGM, what we find is that the droplet receives persistent kicks in the opposite direction, which eventually reverses its walking direction before the waves can decay significantly, so that when it comes time to accelerate again, the droplet already has a small walking speed in the opposite direction. So in the next cycle, it will accelerate in the opposite direction. So this cycle repeats and we get the back and forth stop and go motion. All right, so now in the fourth and fourth SGM, we have a similar thing going on during the acceleration stage. So during the acceleration stage, here also the droplet is bouncing in a 1-to-1 mode, which is able to excite the wave field and allows the droplet to accelerate. But during the deceleration stage, what we find that in the fourth and fourth SGM, the wave field of the droplet decays significantly during the initial stages of the deceleration. So what this means is that the wave field has decayed and the droplet no longer feels the force from the underlying waves. So the only force acting on the droplet at this time is the drag force from during the contact with the waves and also the aerodynamic drag. So this drag force decelerates the droplet, but the drag force can only decrease the speed and cannot reverse its walking direction. So we see a decay in the speed, so speed getting very small. And then when it comes time to accelerate again, the droplet still has a small walking speed in the same direction as the previous cycle. So during the acceleration stage then, the droplet will accelerate in the same direction as the previous cycle and will get the fourth and fourth motion as opposed to a back and forth motion. So in this work, we looked at SGM inspired from a slight detuning of two frequencies that results in the phase difference varying linearly with time. Now, using the back and forth and the fourth and fourth SGM as building blocks, one may be able to guide the droplet into performing more complex locomotions by appropriately engineering phase difference, so a delta phi as a function of time. Hence, it might be fruitful to not only look at delta phi varying linearly with time, but also look at what would happen in situations in which delta phi was allowed to vary with time in a more general way. Moreover, walkers and superwalkers, they have been shown to exhibit novel behaviors when you have interaction between multiple droplets. So it'll be interesting to see how multiple droplet interactions take place in this SGM regime, where the interactions between the droplets, so the interdroplet interactions, will dynamically vary with time, and that may result in novel multi-droplet behaviors. So in conclusion, we showed that driving a fluid bath with slightly detuned frequencies, so F and F12 plus epsilon, results in a stop and go motion for superwalking droplets. And by numerically investigating the parameter space, we found that for relatively small droplets, we either get no walking or irregular stop and go motion, while for relatively large droplets, intriguingly, we get a back and forth motion where the droplet reverses its walking direction after each cycle. and a fourth and fourth motion where the droplet maintains its walking direction after each cycle. And we find that the back and forth motion is typical for negative detunings, while the fourth and fourth motion is typical for positive detunings. And using these back and forth motions as building blocks, one may, in principle, be able to get the droplet to perform more complex locomotion by looking at varying the phase difference in a more general way. So that'd be an interesting direction to explore. Thank you for listening to my talk. I hope you enjoyed it and learned something new.